Okay. So last year's we did discuss about what interface, how the interface is used, and then what is the use of mod ports, module ports, and then clocking logs. So interface, what is the reason to use interface means we are connecting individual signals. Okay, so we need to have all the wires and then connecting together. That would be somewhat difficulty, right? So to avoid that difficulty, we are using the interface. In interface, all the signals are grouped together. We will pass the handle of the interface handle in your module and your test bench. So then all the signals automatically is fetching. And while adding the signals and removing the signals from the interface, it is easy. Compared to the module, suppose if you want to add the signal in your module and remove the signal in your module means entire module code you need to change. Okay. So to avoid that problem, we are using this interface. Okay. And now mod ports. Mod ports is used to direction, giving the direction to the ports, like input ports, who is driving, and then output ports, who is sampling. Okay. From the test bench to and then DUT and DUT to test bench, how we are driving the signals and how we are sampling the signals, it will tell you that mod ports. In a driver, whatever the DUT ports are there in reverse direction, we need to connect that because from the driver to DUT, some inputs are coming and then DUT to driver, some outputs are taking. Okay. So and then monitor in monitor mod ports, all the mod ports are represented as an inputs because it is observing only. It will never drive the signals to the DUT. Okay, whatever the signals are coming from the DUT, so it will observe the monitor. Okay, so that is the reason all the signals are represented as an input only. And then drive DUT ports. DUT ports, input ports, and output ports we need to represent that. After that, here also mod ports, the driver and then DUT, so our multiple drivers are driving the same signals at a time, we will get the race condition. So to avoid that race condition, we are using this clocking blocks. Okay, clocking blocks, some default input 1 nanosecond, output 2 nanoseconds, we are mentioning that. Okay, that means the input signal will be sampled one clock cycle before that, and then output signal to be driven so after two clock pulses. Then we are avoiding the race condition. Okay, so that is the purpose we will go for the clocking blocks. Okay, monitor clocking block, driver clocking block, and then DUT clocking block. So different clocking blocks we are taking. And then next, today virtual interface. Okay, what is virtual interface? Actually, we have two different natures, like dynamic nature and then static in nature. Our static world means whatever the modules we have, all the modules are static in nature. Okay, so that is the purpose we are taking this virtual interface. This virtual interface differentiates that two different natures like dynamic world and static world. Okay, so that's what I want to show you. What is the virtual interface? So virtual interface, suppose we need to understand what is the static world and what is the dynamic world. Okay, static world, what all the modules we have, module, interface, and then some DUT signals, all these signals are related to static world. Okay, so that's what we are saying that because the module is never changed, right? Once you design means the module is fixed. Okay, that is the static world. So then interface also we are representing different signals. Then interface we have different type of signals are grouped together. That is also static in nature. The nature will not be changed. But then how we are communicating with this dynamic world like classes. In test bench we are using the classes. Class is a dynamic in nature. Okay. Then how I need to connect that? I don't have any connection. That is the reason this virtual interface never drives the signals, but it used to communicate between the two natures called dynamic nature and then static nature. Okay, so that is the purpose we are using this virtual interface. See, your classes or objects or UVM components all are in dynamic world like TB world. Okay, test bench side we are having, right? So in this test bench, all the signals are representing. Okay, so that means we are driving the signals. See, the driver is driving the signals and generator is generating the signals. All the signals are dynamically created. So because the new method is creating that memory or object, so that is in dynamic in nature. Okay, so to communicate with that, so this dynamic in nature, like the problem is DUT signals are inside the interface, and then classes want to drive them, then we are getting some error. Okay, so because without interface, without virtual interface, we can't communicate with the dynamic world and static world. Okay, so that is the purpose we are going to discuss about this virtual interface. See, just here we are having some DUT signals. What is the interface signals? Bus interface, logic request and logic grant. And class want to drive them. Okay, like driver class we are taking that task run and then request equal to 1. Okay, directly we are giving the request equal to 1 is giving that error, because how does a class knows that the request is there in your interface? We don't know, right? We are representing the signals in our interface. Those interface signals are communicating with the class dynamic classes. So then class doesn't know, so we have the signals or not. Okay, that is the reason we are getting the error. Okay, so it is showing that the question is, how does a class knows that where request is existed? Okay, it doesn't know, because the class it lives in a dynamic world and an interface lives in a static world. Okay, so the problem is there is no direct connection. So to avoid that problem, we are using this virtual interface. Okay, system Verilog created that virtual interface. Okay, so then think it as a virtual interface is like a pointer. That pointer will point out different signals, and we will get that signals through that pointer. Okay, so that's what. Think of it as a pointer to an actual interface, just like class handles points to the object, right? So how we are representing the handle for the class packet I am representing. Okay, for this packet in my module test bench, we are taking this packet. For this packet, I am representing the handle. Whatever the properties in your classes, okay, so address and data we are having, right? So all these address and data I am calling through this packet handle. Okay, so initial begin, I am taking that. Okay, so packet ticket equal to new. Based on that object is created, then packet dot address equal to some value you are assigning that hexadecimal AB, and then packet dot data, okay, 16-bit hexadecimal, some 5555. Okay, so this way we are getting the signals in your TB, right? Same way, whatever the interface we are having, like so before that we are using this virtual. Okay, virtual some app interface we are taking that. For this app interface I'm using the handle called virtual interface VA. Understood, right? So same thing, just what is the interface in syntax you are taking that interface. Okay, some app interface you are representing. Inside that logic some signals we are representing, like P address, okay, P data. In this way, you are representing the signals. All the signals we are getting through this handle, virtual interface handle. Okay. So this is the basic interface. See how we are representing the interface signals. Interface name, logic, request, and grant we are representing. So this is my interface, bus interface. Inside that, all the signals are representing. Then virtual, what is your interface name? Bus interface. Then bus interface handle is VF. Okay, remember that virtual interface doesn't create any hardware. Okay, they will ask you virtual interface, does virtual interface create the hardware? Then your answer is exactly no, because the virtual interface, you are assuming that there is a child in front of you, but you are assuming, assumption is not the physical thing, right? So assuming in our mind, okay, I'm thinking I need to sit on a chair. Okay, so then the chair is physically not available. Then how we can represent that? So in that way, the virtual interface is accommodate that, the combination accommodation, just like a friend's room. you came you came to Bangalore and then you don't have any facility to accommodate it, so you don't want to go to that restaurants and hotels. So then your friend is giving the accommodation, virtually is providing that. Okay, so like that room is not yours. Okay, physically it is not for you. Okay, someone's room you are living for a temporary purpose. Okay, same way this virtual interface is also giving the accommodation only. So through virtual interface, we are calling that. So virtual interface declaration, how we are declaring virtual, some APB interface or multiple interface, then VF we are taking that. This VF, no interface is connected. Still, it is not connected to anything. Now you are initializing that interface equal to VAF. Okay, that means your interface should be connected to virtual interface. Now this physical interface pointing that virtual interface. Then virtual interface pointing that physical interface. Now whatever the signals are there in your physical interface, through virtual interface I can call it. Okay, here that's what. See, previously directly a I am giving the value. Okay, in my driver, so a is a signal, a equal to 10 I am giving, or a equal to 1 I am giving. That gives you the error, right? Because you don't this interface or module TB doesn't know this signal is where it is coming. Okay, because all the signals are represented in interface. Then I don't know where it is coming from the signals. That is the reason it gives you the error. Now you are pointing through virtual interface. VF dot A equal to value you are assigning them. Then this signal will be pointing to the virtual interface. That virtual interface pointing to that, see, virtual, you are representing some multiple interface. Okay, so we have this virtual interface. Suppose you are driving the signals like this, VF dot A equal to 1. This A will be pointing to the virtual interface, then virtual interface pointing to the multiple interface. So this multiple interface pointing to this physical interface. Backward, back tracing. Virtual interface to signal to virtual interface to physical interface, and physical interface to inside the signals, whatever the signals you mentioned in your physical interface, those signals will be getting. Okay, so then just physical interface, and then your class driver. In the class driver I am representing the virtual keyword, through virtual keyword, the physical interface representing here. Okay, this is the physical interface. Okay, this is the virtual keyword. Based on that, it should be converted to virtual. For this, I am taking the handle for my virtual interface. Okay, understood, right? Then I can access the signals inside the physical interface through virtual interface handle. Like VAF dot request equal to 1 or VAF dot A equal to some A comma request comma A comma B comma C signals are there. VAF dot A equal to some 10 and VAF dot B equal to 20 and VAF dot C equal to some 30. These values are driving here. Okay, understood, right? So how then this will know, this driver will know, okay, I'm having some virtual interface handle. Okay, this virtual interface pointing to the interface. In that interface, I'm having the signals. Then I will get that signals in my driver class. Okay, this is the way we are instantiating. See, interface is directly assigned to driver.behavior. Then driver, whatever the signals are driving, those signals will be appeared in your test bench. Okay, so the test bench will getting the different signals. Then we are running that driver.run. So run is the task we are writing in your driver. In that task, whatever the signals are there, all the signals will be running together. So constructor initialization. So you know how in virtual interface, whatever the virtual interface we are taking, in constructor also we are passing some arguments like this. See bus virtual interface. So VA virtual bus interface VA. This interface I am passing in my constructor. So this keyword will differentiate that functional arguments and class properties. Then I am using the same name for this virtual bus interface VAF. Here also I am using the VAF and here also I am using the VAF. Then VAF equal to VAF you are mentioning means then you simulator will be getting some confusion. Okay, because which one is the functional argument, that means constructor argument, and which one is related to your class number. So then this keyword will differentiate the global properties and functional arguments. This is your constructor argument. Okay, constructor argument, and this is my class property. Okay, so this keyword will differentiate it. If you don't want to use this keyword, then name it different. So virtual interface like VINTF or VAF handle. Okay, something VAF some handle. In this way also we can represent. Now these two handles are different. Okay, handle names are different. In your constructor, I am using that VF handle, and your class VF I am using. Then both are equating together. Then there is no conflict we are getting. How we are equating VF equal to VF handle. In this way, I am equating them. Then I will get all the signals properly. Okay. Same thing. So bus interface where driver DRV initial begin. Through constructor I am calling the interface. DRV equal to new of where INDF. So this INDF is the bus interface handle. So this bus interface directly calls to this VF. Okay, understood, right? So constructor how I am getting that. So this is the actual interface. So through constructor we are calling the virtual interface. In this way we are calling the virtual interface through constructor. Constructor pointing that physical interface, this physical interface going to the constructor handle, this constructor handle is pointing this virtual interface. Okay. So reading signals through virtual interface. How I am reading the signals? Through vf dot request equal to some value and vf dot request equal to some dsn the value. Okay, we are driving the signals. Okay, that is the reading the signals. See, interface. This is my physical interface. In this grant I am mentioned and monitor. Monitor is observing the signals. See, vf dot grant we are observing. Okay, so through virtual interface we are getting this grand signal, then reading the signal. Monitor is always reading the signals, not driving the signal. Driver is always driving the signals. Okay, so here I am using the driving signals through virtual interface. So here I am driving the signals. Okay, monitor always access the DUT signals through VA. Through virtual interface only, I am accessing the all signals in my test bench side. Like multiplier interface I am taking here. Driver is driving the signals. In task run case, I am driving my signals like vf.a equal to some 10, vf.b equal to 20, and giving. So this is my interface signals. So in interface, I am driving the I am representing all the signals A, B, and output signal. Okay. So in this is my module DUT. In that module DUT through interface, I am assigning the output like intf dot equal to interface dot A into interface dot B. That means multiplication I am doing here. Okay, two signals are multiplied together. Then you are driving the signals vf dot a equal to 5 and vf dot b equal to 5. That means it is pointing this interface dot a into interface dot b. Okay, so then a value is 5 into b value is 6. Then you are getting 30 is the output. Then driver is displaying the AB values and then monitor reading the input values. Then your output will be displayed at the monitor side. This is my test bench. And then test driver driving the signals. And in my test bench, I need to represent the interface handle and then virtual interface handle. After that, some multiplier instantiation based on that. Through constructor, I am assigning the interface handle to driver and then interface, physical interface, same constructor I am using. And then I am running the driver task run phase. So during this task run, I am calling through this driver handle because this class driver handle I am representing in my TB. Okay, DRB. DRB equal to new of INTF. Then this constructor new method VF is there. Then VF will be equal to INTF. Okay, interface handle. Okay. Then physical interface is showing that all the signals will be communicate each other. Similarly, randomization I am applying that. So in interface also, sorry, in class we are randomizing the signals. Previously I am passing single signals like A, B. Okay, in my driver, whatever the signals are there, I am driving the signals. Those driving signals should be randomized. In driver also you can represent, or in transaction class also I can declare my signals through randomized way. Okay. So in task run phase, I am setting the randomization. Then whatever the signals we are driving through virtual interface, all the signals should be randomized. Okay. So based on that, different values will be getting because you are repeating 5 times. Then 5 times, 5 different values will be appearing because you are randomizing the signals. This is the syntax for randomizing the signals. Repeat of 5 means A equal to some 5, B equal to 10 in one case. A equal to some 115 and B equal to 110 and C equal, so these are the values we are representing. Then passing virtual interface to multiple components. We can pass that virtual interface to many components like driver we can pass, monitor we can pass, and scoreboard also we can pass this virtual interface. Because you need to remember whatever the DUT is there, this DUT will be communicating through driver. Okay, so driver is driving the signals to the DUT and DUT sometimes also driving the signals to the driver and monitor is connecting here. Okay, so monitor is always observing the signals. This monitor is connecting to scoreboard. Okay, scoreboard is comparing these output signals like these are the signals called actual signals. Okay, actual output, and then here also I am having some input monitor. Okay, this input monitor is getting that reference output or expected output. This expected output and then actual outputs compared by the scoreboard. If both are equal, then your test bench will be passed. Okay, so this is the connection. So in entire test bench, driver is connecting to the DUT and DUT is connecting to monitor. Okay, through this only we are communicating the signals. Okay, that is the reason we are passing the virtual interface to multiple components. Okay, in virtual interface we are also using the mod ports. Mod ports gives you the direction to the ports, module ports. Okay, here I am using the driver. That means whatever the DUT signals, input signals are there, all the signals should be become output to the mod ports driver. And whatever the output signals in your DUT, that should be inputs to the driver. Okay. See, request is the output and grant is the input. In your driver class, I am passing this virtual keyword. Then bus interface dot driver VF, because in mod ports we are driving this. Mod ports, my mod ports name is driver. Through driver we are calling the signals, because in module ports we are declaring the direction of the signals. Same way we can also apply the clocking blocks. Same mod ports we are applying that, and then clocking blocks also we will use that in interface. Okay, in interface clocking blocks I'm using. Clocking blocks, it calls that your mod ports driver or monitor, mod port monitor we are calling through this clocking block. Okay, this clocking block will drive the signals before the sampling, before the clock edge or after the clock edge. Based on that, it will be avoiding the race condition. Okay, so same thing, the clocking block at the rate passage clock, my output request will be driving here and then sampling the grant. Okay, so the driver through clocking block we are calling vf.cb. This cb will drive this request and grant. Okay, so vf.cb.request equal to 1. Previously vf.request equal to 1 I have called. Okay, now clocking block I am using. Then vf dot clocking block dot int request equal to value you are driving. Through clocking block we are driving. And previously mod port vf dot driver dot vf some signal request we are calling. That means mod port driver name we are calling through that um, in your interface. Okay, virtual interface. This is the clocking block and mod ports. Okay, and then we are setting the config db. ConfigDB is a configuration database. It is a centralized database. Okay, we are setting the centralized database in your top and calling in the below test bench components. Okay, so that will be explained in your UVM. So in UVM we will get this virtual config DB and resource database. Configuration database follows that hierarchy, and resource database is a global representation. Wherever you want to set that global representation, this resource DB will be setting there and getting that different components. Okay. Just see this summary. So the next topic is system verilog scheduling semantics. Scheduling semantics means what is the signals we are having. Those signals, all the signals are executing at zero simulation time, right? In your DUT and then test bench, we are driving the signals through the test from the test bench to DUT, and then DUT is executing that signals. All the signals are executing at the zero simulation time. In your test bench, we are representing different initial begin blocks. All the initial begin blocks are executing at zero simulation time. Then we may get some race conditions. To avoid the race condition and understand some assertions and where the signals are driving and where the signals are sampling. Okay, all these signals, all these things are understood by using system verilog scheduling semantics. These are also called as regions. Okay, so different regions. You know already active region, inactive region, NPA region, and postpone region in Verilog. Okay. Same way, here also some 11 regions are there. All these regions, that means extension of the regions in your Verilog, the system Verilog will gives you some prepone region and postpone region, pre-active region, post-active region, pre-inactive region. So all these regions are comes into the picture. Okay. So then these based on these regions we will understand that which region is executing that active components, that means active statements are there, right? So active region, in active region what type of blocking statements are executing or non-blocking statements, right hand side part is evaluated, and then so it is updated the value in the NV region. Okay, you need to understand that most of the code is executed in active region. Okay, because this active region only all the test bench codes, whatever the test bench codes are there, all the codes will be executed in active region because blocking assignments, non-blocking assignments, and display statements, all these things are executed in active region, right? Initial begin blocks, okay, and the events, whatever the events are there, all the events are also executed in active region. Okay, most of the codes will be executed in active region, and then remaining parts are there. Those parts will be executed in different other regions. See, this is what is the scheduling in system Verilog. Actually, simulator executes that statements within a single time slot, right? So based on that, we are executing different signals like this. Okay, um, just t equal to 0 second only, it is executing all the statements within a single time slot. This is my clock t equal to 0 and t equal to 10. This time slot only it is executing all the signals. That means at t equal to 0th time only all the initial begin is there, right? This initial begin end inside whatever the statements are there, all the statements are executed at t equal to 0th simulation time. Okay. So that is the reason Most of the times we are getting some race conditions or unexpected outputs, sessions behavior, unclocking block behavior, and UM synchronization issues. So without understanding these regions and which region, which type of statements are executing, we don't know means we may get trace conditions. Okay. To avoid the trace conditions, we are using this scheduling. Okay. So why do we need scheduling semantics? See, always at the rate postage clock, some blocking assignment, and always at the rate postage clock, some blocking assignment. Okay, at the same clockage, I am driving A equal to B. That means B value is assigned to A. And then same clockage, A value equal to B. So that means so B equal to A. So A value is assigned to B. That means whatever the value I'm having, that value will be assigned to in your handle, in your value case, and whatever you are having the value, that value is assigned to me. That means swapping of two numbers is taking place. But on the same clockage, the simulator will see the previous value only. Suppose you are taking this A equal to 5, okay, and then B equal to 2. That means if A equal to B means B value will be 2, right? This 2 value will be assigned to A. Then A equal to 2 and B is also equal to 2. Then simulator will see the previous value only, not the current updated value, because we are not applying the non-blocking assignments inside the always begin block. If you are assigning that non-blocking assignments, those are executing parallelly. Then, at a time, without any conflict, those two values will be tried. Okay. So previously non-blocking assignment, this will be executed. Then the same clockage we are passing the another value, but same clockage previous value we have driven. Okay. That value only simulator will see. Okay, so that is the reason we may get some conflict, because I want to see A value in B, B value in A, but I am seeing the only B value in both A and B value. Okay, so then swapping is not possible. To avoid that, we are using these regions. Okay. See, at the same clockage, within the block executes that first process 1 or process 2 without defining the order, because both those two always begin blocks are executed at same time. Okay, so then simulator becomes unpredictable. To solve this problem, system verilog divides this every time slot into multiple ordered regions. Okay, so same time I'm driving the different signals means then my system will be getting some confusion state. That gives you some race condition. Okay, to avoid that race condition, I'm going to schedule that different regions. These regions, see, just I'm the one person to consult different people. Okay, at a time all the people are come near my office and then they want to visit me. So then there is no use of that, because all the persons are talking at same time. You are talking different topic and she is talking another topic and then she is talking another topic. Then I don't listen all the values, all the things at a time. In class also, teacher is asking something means all the students are talking together at the same time. Then I didn't understand what you are talking, right? To avoid that confusion, I am asking individually. Okay, first I am asking you, then your answer I am listen properly. After that I will go for the another person answer. Okay, so based on that I will listen all the answers clearly. Based on the time slots I am assigning, right? So here also system verilog gives you some time slots. See, t equal to time equal to 100 nanosecond. It is moving to 1 second. Before that only, all the regions will be executed. Within 1 nanosecond, active region will be preponed region will be executed. Reactive region is executed. Active region is executed, and inactive region is executed. Pre-NDA region is executed. NDA region is executed. All the regions will be executing one time slot only. Then how they are accommodating? That is the problem. Okay, based on that we are simulating the different time slots. Okay, so we have different values here, different regions. All the things will be executed in different regions. So simulator does not move to the next time until all regions finish. So if you are finishing the all regions, then only simulator is moving to the next time. Okay, understood, right? What is the use of preponed reasoning? Assertions are there. That immediate assertions are there, concurrent assertions are there. All the concurrent assertions are sampled here only. Okay, sampled that A B values. So all these signals sample the values before anything changes. The main usage is here is current assertions. Okay, to evaluate that current assertions. So assertions evaluation and updation will be taking place two regions. In preponed region. Okay, what is the purpose we are using the preponed region? Sample values before anything changes. If you want to change the values, okay, before that it will sample. That means it will see the output. Then, if you are changing the value, then the changed values are also it is seeing in the next time class. Okay. Main usage is concurrent assertions. That means delays in the assertion. See, this is the implication operator. Next clock edge, it is evaluating. Okay, so that's what. As set property at the rate posage clock, A is high. In the next clock cycle, B is high. Okay, so in preponed region, the assertions are sampled. The concurrent assertions are sampled in preponed region. Remember that. This preponed region, what is the main usage is concurrent assertions are sampled here. Okay. So when the clock arrives, the preponed region samples that A and B values before update occurs. Okay. That means you're changing the A value to 5, B value to 10. Previously, A value is 2, B value is 3. So that values I need to evaluate first, sample first. Then the other values will be sampled. Okay. So this is the before simulation. If you want to sample any value, this preponed region will be taking place. This concurrent assertions will be sampled here. Okay. Think a photograph before anyone moves. Okay. So while moving something means I am capturing the image, then my image may get blurred. Before standstill position only, I will take the picture. Okay, then I will get the picture properly. Then you want to move it, then move it. Okay, so that's what it is saying that preponed region. Mainly preponed regions are used for concurrent assertion sampling. Okay, and pre-active region. Okay, so pre-active region means we are using DPIs, direct programming interface, and PLIs, program language interface. Okay, programming language interface, and DPIs means the CPU doesn't understand whatever the system verilog code you are writing. Okay, it understands only the C language codes. Okay, I need a translator. Okay, this DPI will translate it. Okay, during that importing and exporting. importing means we are uh, converting that system verilog language into C language and C language to system verilog language. Okay, this conversion will be taking place in this pre-active region. Okay, so pre-active region PLIs and then DPI callbacks are rarely used in RTL. Allows simulator tools to inspect the values before the active region. Okay, so whatever the DPIs and PLIs we are using, right? Those values will be converting before simulation only. It is converting that. Okay, then it will be talking together. Okay, so I'm the Japanese person, you are the Indian person. I'm talking something with you. Okay, you didn't understand because I'm talking in a Japanese language and you are talking in a Telugu language. Okay, then I didn't understand. Then I need a translator. This DPI will be translated there. Okay, programming language interface is also translated. Same thing. Next, active region. Active region, all the blocking statements and dollar display statements, and then NBA non-blocking statement RHS side will be evaluated here, and then updation will be done in the NBA region. Okay, so that is the active region. See, remember, most of the times they are giving like snippets like this: A equal to 0, B equal to 1, then A equal to B. So which value will be displayed here? Okay, so the last updated value will be assigned to here A equal to B. B value will be 1. Then A is also seeing that 1. All the blocking statements are executed in this active region, and dollar display statements are also executed in this active region. And sometimes A less than or equal to B I am taking, this B value will be evaluated in this active region. Okay, remember, everything happens immediately in the active region. So that means all the regions, all the codes are executed in the most of the codes are executed in active region. See, see, RTL execution. Most of the RTL codes are executed in this active region. Okay, so most of the RTL code is executed here. Always, initial, continuous assignments, and blocking assignments. Continuous assignments and blocking assignments both are same, right? Blocking assignments are used for continuous statements. Okay, continuous blocks. And then continuous assignments, which blocking statements are using. And dollar display statements. Okay, so dollar display statements are also executed here only, and then non-blocking RHS of the NBA values, that means non-blocking assignments. All the things are executed in this active region only. Okay, so RHS evaluate. See, this is the non-blocking value. RHS evaluated in this active region only. Later, this LHS will be evaluated, updated in this NBA region. Okay. Now you have seen this blocking assignments, that means continuous assignments. Okay, and then some assign statements. Assign A equal to some C and D. Okay, these assign statements are also executed in active region. That is the continuous assignment. And inactive region, hash zero statements will be executed. Previously you have seen, right, A equal to B and B equal to A. So then before that you are applying that hash zero statement means then A equal to B and B equal to B value, swapping of two numbers will be executed, because this hash zero statements avoids the race conditions, avoids the race condition, and it will be taking that some blink it time. Okay, blink time, it will be executing the two statements. Okay, then A equal to 1 and then hash 0, B equal to 1 we are taking here. So both will be executed. So in this active region. So this hash zero statements are executed for used to avoid used to avoid race conditions. Okay. So why delays are execution without advancing simulation time? Because um, this active inactive region hash zero is not giving the delay. Okay, just a small second delay is only provided. That is the reason it is executing here. Okay, so delay execution without advancing the simulation time. Okay, so hash zero is the delay execution, but it's not giving any further delay. Just you started from your house and then someone is calling back. Just you are crossing the gate and then your money is going. Same thing will be happening. Okay? And then pre-NBA reason. Pre-NBA reason mainly PLI callbacks. That means programming language interface callbacks we are executing here. Okay. So most of the times we are not using in your RTL. Okay. So rarely visible in the RTL side. Okay. Most of the times we are using in testnet side only, PLIs and DPIs. That is the reason. So these values will be appeared in the testnet side. RTL side rarely we are applying that. Okay. So this is the just before the NBA updates. Pre-NBA reason means if you want to update the values in this pre-NBA region, I told you pre-code region, that means pre-randomization, post-randomization. Before randomizing, you want to see some values, pre-randomization will take place. And then randomization, we are using the randomization and you want to display the randomized values. And post-randomization region, we are seeing the randomized values outputs. Okay. Same way, pre-NBA region, the NBA region, non-blocking regions values will be updated, right? So whatever the LHS values are there, all the LHS values are updated in this NBA region. That assigning will be done in the pre-NBA region. Okay. So pre-NBA region, all the things will be settled. Okay, that is checking that. So just occurs before the NBA region. Then most of the codes, PLI callbacks, all these things are executed in this NBA region. NBA means non-blocking assignments. Then all pending updates. So updates occur here. That means whatever the active region, the evaluation is done, right? Non-blocking assignments. That updations will be taking place here in this NBA region. That means at t equal to 0, the active region will be taking place. And moving forward, some t equal to 10, in this only inactive region is there, and NBA region is there, and pre-NBA region is there, and then post-NBA region is there. Okay, so based on that, different regions will be executed here. Okay, why NBA exists? Because NBA makes the simulation behaves like a hardware, like we are creating the hardware, right? Whatever the things we are writing through this NBA region, we are creating the hardware. Then the values will be updated here. Okay. So then whatever the flip-flop values we are taking or latches, all these things are updated here only. Okay. So real hardware, both the flip-flops are sampled simultaneously because so these two values are sampled simultaneously. Then NBA makes simulation behaves like a hardware. Okay. So whatever the hardware is working, how the hardware is working like same thing and there is in the taking care of them. Because all the things are executed parallelly. Simultaneously executing means parallelly executing. That is the reason real hardware how it is executing like that. Only this NBA region will be executing all the statements. See, A equal to B and B equal to A. So A equal to 1, B equal to 0. After the clock is A equal to 0, B equal to 1. Then swapping will be happening. Okay. And then post NBA region. Post NBA region is nothing but executes after the NBA region. The updates will be happened here in this NBA region, right? Then, if you want to use any callbacks, you can apply here in this post NBA region. Okay. So mostly used by tool and callbacks. Okay. So this post NBA region tool may be utilizing that. That means internally it is operating, not seeing the externally, like that. Okay, suppose synthesizing is done, we are seeing the net list. What happens internally we can't see, right? So that will be executing in this post MBA region. And observed region. Previously, preponed region, the assertions are concurrent assertions are taking place here. Okay, so now the evaluation of assertions will be sampling will be done in your preponed region. Okay, sampling that values will be seeing the outputs. Okay, that preponed region will execute this um, what it called assertion sampling will be taking place. That assertion sampling is done, and then output evaluation will be done in this observed region. Okay, so observed region concurrent assertions are evaluated here. In two regions, assertions are taking place. Okay, sampling will be done in recon region, evaluation is done in observed region. Okay. See, this is the property name at the rate postage clock. Request is high, and then after one clock age, grant will be high. This evaluation will be done in observed region. Okay, so observed region, also all the assertions evaluations will be done here. Why not active? Because needs final stable values. After all the NBA updates, it will be executed. Okay, he is asking you why these assertions are not executed in the active region, because the assertions are checking that is that output is getting correctly or not. Then I want to execute all the statements in active region and NBA region, then go for the observed region. In this observed region, that output is happening properly or not, I am checking here. Okay. And then post observed region. Any assertions fails or callbacks fails, assertion pass or fails and callbacks, the tools we are using, right? So then all these things are executed in this post observed region. Observed region, your assertions will be evaluated, and then uh, post post observed region. In this post observed region, your assertion is failing or assertion is passing. It will check that is this your assertion is passing or not. Okay, where it is passing and where it is failing. This pass or fail conditions will be checking by this post observed region. Okay, and reactive region. Reactive region. What is the main purpose we are using this reactive region? Programming block is there. Okay, why this programming block is there means it will coming in the next slides, further slides. Okay, programming block actually we are using that some test bench execution. In the test bench and DUT, the same values are passing, right? So at that time, race condition may occur. To avoid that race condition, we are using this programming block. This programming block is executed in reactive region. So this reactive region, all the active regions, NK regions, observed regions, all the regions are executed. Then it is going for this reactive region. Then this programming block, whatever the code piece of code you are writing in programming block, that will be executed. Okay. So then it avoids the race conditions. It is executing in a smooth way. So to avoid the race condition between the test bench and RTL, we are executing the different signals in the active region, right? So this reactive region, uh, what we are taking programming test, initial, begin, and end program. That means whatever the test bench writing the code, so same thing will be updated in this programming block. Okay. So this programming block avoids the race condition between the test bench and RTL. Okay. So RTL is executing first, right? Then test bench reaches later. Hence, reactive region will be nothing will be creating the race conditions. Okay, because in active region only all the program is executed, and remaining things are there. Then go for the inactive region, and then go for the NBA region. After that, post NBA region is there, and then pre NBA region is there. So after that, we are going for this reactive region. Okay. Then this is the postpone region. Postpone region means dollar monitor, dollar stroke, dollar right, whatever the statements are there. All these statements will be display statements will be executed in this postpone region. Dollar monitor, it will continuously checking that whatever the values are updated, right? And postpone dollar stroke, last updated value. So whatever the last updated value is there, that will be executed this dollar store. And we also executing the coverages. Hmm. Coverage codes we are writing. That coverage will be updated in this postpone region. Okay. Coverage means your functionality is that executed properly or not, and your code is executed properly or not. We are checking that. Okay. This is the dollar stroke symbol. So last updated value is there that will be executed in this dollar stroke. Okay. This is the complete timeline example. See what are the things are executing here. This is what non-blocking statement. This B value will be evaluated in which region? Active region, right? And then C equal to D will be executed in active region. Okay. And then see B is reading for active region and scheduled in this NBA region. That means updation A value will be updated in this NBA region. Okay, and read D updates C equal to D. Okay, so blocking statements, non-blocking statements, and then active region, all the blocking statements are executed, and then right hand side part is evaluated in this active region. That means non-blocking statements, right hand side part is executed in non active region. Okay, and whatever the continuous assignments like assign statements are there, all these things are executed in active region. See, updates A is happening in NB region. Any assertions are there evaluated in observe region. And then postpone region, monitor, slow, and then coverages will be updated in this postpone region. Understood, right? Okay. The regions are very important. Whatever the regions we are using, based on that, prepone region, all the assertions will be sampled. Okay, and then active region. Okay, in this active region, all the blocking statements and then continuous assignments and then uh, dollar display statements, all these things are executed in this active region. And inactive region. Inactive region, we are having hash zero statements. Some delay less statements will be executed in this inactive region. Okay, so we have NB region, pre-NB region, and post-NB region. Pre-NB region, any evaluations and fallbacks and PLIs are there, the tool will be executing here. Okay, this pre-NB region. So all the exceptions will be evaluated in this NB region. Whatever the things we are using, updation of the values. Okay, A equal to B, A less than or equal to B, we are representing. That values evaluation will be taking place this NBA region. Okay, and then post NBA region. Post NBA region, we are taking that some tools called that some object values, coverages, all these things will be executed. Okay, and then observed region. So this observed region is the new region compared to that verilog. Okay. So, assertions, evaluations will be taking place in this observed region. Okay. In reactive region, this reactive region is also there. Reactive region will be executing this programming block to avoid the race conditions. Okay. Remember. Some postcode region. Postcode region, anyways, you know, dollar monitor statements, all these things are executed. See, one code related to this one. Just take 2 minutes break. See, take time scale module scheduling semantic demo. So here, clock and A, B, C values are taking. Okay, and then clock generation. Clock equal to 0 forever. Clock equal to negation of clock. See, preponed region, observed region, concurrent assertions will be executed, right? So this is the assertion. A will be uh, high after one clock edge, so B will be high. Okay. So at the same clock edge, B will be high. Okay. So that asset property, the property name is pj, and display that observed region assertion passed or failed. Okay. And then active region. In active region, what are the things are executing? So region starts that A equal to negation of A. So this is the blocking statement. So that means A value will be negation. Previously, what is the value I am assigning that? Nothing. Then 0 will be taking place. Then A value will be toggled. Okay. I will get that A value will be 1 here. And then NBA region. In this NBA region, the evaluation will be happened in this NBA region. See, active and scheduled at that NBA region. Okay, and another related to NBA region only. An inactive region has zero statements are executing. Okay, so to avoid the race condition. Reactive region. In this reactive region, we are using this final blocks only, demonstrating inside the module. And note that true reactive region requires the programming blocks. Programming blocks cannot be declared inside the module. Therefore, reactive region cannot show in one module. Okay. So that means reactive region is executing all the programming blocks, right? So to avoid the race condition. Hmm. So then this is also executing, and then this double hash zero means assertions, SVA. Okay, so delays will be taking place. And then postpone region, dollar monitor statement and dollar store. Initially, I am assigning the values, all the values should be 0. And repeat of 5 at the rate passage clock, then finish and calling. See, check this output. 5 times you are repeating, right? So one output you need to check. Okay. So region start. In the active region, the region start is there, right? Hmm. This is the active region start. Okay. During the active region, blocking assignments. What is this blocking assignment? A is equals to 1, you got it. Because initially A equal to 0, I am initiated. Then A equal to negation of A, we are executing. And NBA region, this B less than or equal to A will be executed. If you want to display the value, you can display it. Percentage 0 B, you can take that, then you will get the display value also. This is also executed in NBA region. Sorry, active region. And C equal to B. This is also NBA schedule. Okay. And then reactive region. Inactive region has zero statements are there. See, this inactive region has zero statements are there. Before that, reactive region is executing. See, this reactive region, whatever the reactive region requires the programming block. Okay, so that will be executed. In active region only all the things are executed. See, inactive region has zero statements and post monitor statements. Dollar monitor AB values, that means postpone region it is executing. Dollar strobe also last updated values. So these are the last updated values. Those values only displayed. Understood, right? So this regions. So this code is available and then you can execute it. So just 2 minutes.